All right, so today we're going to talk about the absolute brain behind the autopilot on pretty much every modern airliner. It's called the flight management system. You know, it's kind of the unsung hero of the flight deck, and we're about to peek inside its digital mind. Let's dive in.
I mean, think about it for a second. How on earth does a massive 400-ton jet fly a path that's accurate to within just a few feet for thousands of miles? It's just incredible, right? Well, the answer isn't just the autopilot. It's the brain that's telling the autopilot exactly what to do every single second of the flight.
All right, so here it is, the autopilot's brain. And that brain, as we've been saying, is the flight management system, or FMS for short. Seriously, the best way to think about it is like the plane's central nervous system. It's this powerful computer that takes a basic flight plan and turns it into a living, breathing, incredibly complex reality.
So, okay, what does this thing actually do? Well, at its core, the FMS is an onboard computer that juggles a few really big jobs. It handles navigation, of course, it crunches all the performance numbers, but the most important thing, the real magic, is that it computes what's called a reference trajectory. And that's basically the perfect, most optimized flight path for the plane to follow, all the way from takeoff to touchdown. Okay, Section 2, a perfect flight recipe. So you might be asking, how does the FMS actually come up with this perfect path? Well, it's a lot like a master chef getting ready to cook a really complicated dish. You can't just start cooking, right? You need all your ingredients laid out first. And the FMS is exactly the same. It needs a whole list of data before it can do anything. And here they are, the key ingredients for our flight recipe. The FMS needs to know, okay, what kind of plane are we? It has to know its own performance characteristics. Then you've got the flight plan waypoints, the basic dot-to-dot route. It needs all the rules for altitude and airspeed along that route. It needs to know the plane's exact weight and where it's starting from. It needs the speeds the pilots have commanded for the climb and cruise. And then there's this last one, which is just wild. It needs a full-on forecast of the atmosphere, so wind and temperature. Okay, check this out because this is where it gets really clever. Let's talk about that atmospheric data. The FMS might only get a handful of wind forecast points. You can kind of see them represented here as these colored dots at different altitudes, so it doesn't get the wind for everywhere. But from that pretty limited information, it builds its own complete, continuous 3D model of the wind for the entire flight. It's basically filling in all the gaps to create a perfect picture of the air it's going to fly through. Just an incredibly sophisticated piece of prediction.
All right, Section 3, drawing the path in 4D. So our FMS has all its ingredients. Now it's time to actually cook up the flight path. And it does this in two main steps. First, it figures out the path across the ground, the horizontal part. Then, it calculates the up and down part, the vertical profile. Let's break it down.
So step 1 is the horizontal path. When you see a flight plan on a map, it just looks like a bunch of straight lines connecting dots, right? A total connect the dots game. But an airplane can't make instant sharp turns. So what the FMS does is it smooths everything out. It calculates the perfect arc for every single turn, figuring out the exact geometry based on the plane's speed and how much it can bank. It's what turns a jagged set of lines into that smooth, graceful path you feel when you're flying.
Then we have step 2, the vertical profile. This is all about the ups and downs. The FMS calculates the most fuel-efficient way to get from A to B. So it plans the perfect climb, finds the best altitude to cruise at, and then, this is the really cool part, it figures out the exact point to start an idle thrust descent. That means pulling the engines back to idle and basically coasting downhill like a giant 400-ton glider all the way down to the approach. It's all about saving every last drop of fuel while hitting all its altitude and speed targets perfectly.
So what happens when you put those two things together? You put the horizontal path and the vertical profile together, and what you get is the final product, a perfect 4D trajectory. That's the key. It's not just 3D. The FMS doesn't just know where the plane should be in space, latitude, longitude, and altitude. It adds that critical fourth dimension, time. It knows exactly where the plane should be and precisely when it needs to be there.
Okay, Section 4, the pilot's critical question. So we've got this flawless digital blueprint for the flight, cooked up by the FMS. It's perfect in theory. But what happens when that perfect plan makes first contact with the messy, unpredictable real world? Well, this is where the human pilot becomes absolutely critically important. And to really get this, we have to talk about one of the most important numbers in all of aviation. It's called V1, the decision speed. During takeoff, as the plane is rocketing down the runway, V1 is the point of no return. Before you hit that speed, you can abort the takeoff, hit the brakes, and stop safely. But the second you pass V1, you are going flying. No matter what, you are committed.
So you can see, the whole concept of V1 is completely tied to physics, and specifically to the length of the runway. As a pilot put it on a forum, and this really spells it out, V1 has to be low enough so that if something goes wrong, like you lose an engine, you have time to react, pull the power, hit the brakes, and get the whole thing stopped, all before you run out of pavement. It's a hard physical limit.
Okay, so that leads to a really logical question, right? It's one a flight simmer actually asked online. If V1 is all about stopping distance, then the FMS has to be using the runway length to calculate it. I mean, it makes perfect sense. The pilot tells the computer which runway they're on, so of course the computer uses that length to figure out a safe V1. Seems totally obvious, doesn't it?
Well, here's the twist, and it is a fascinating one. The answer from the pilot was basically this. Nope. The Boeing FMS, it doesn't take runway length into account at all when it calculates V1. It just assumes you have enough runway. It calculates V1 based on other things, like weight and the air density, and just trusts that the runway is long enough to handle it.
So what does that tell us? It tells us that the FMS is an unbelievably powerful tool, but it's not infallible. It has built-in assumptions. And this is why in real-world flying, pilots never just blindly trust the speeds the FMS spits out. They always double-check them with external charts and performance tools to make absolutely sure those speeds are safe for the actual runway they're on for that day in those conditions. The human pilot is always the final essential safety check.
All right, Section 5, Flying into the Future. You know, that whole B1 example is a perfect illustration of the partnership between human expertise and automated precision. And it's that precision that is paving the way for the entire future of aviation. So, why does having this perfect 4D trajectory matter so much? Well, it's not just about one flight. It's about the foundation for the entire global air traffic system.
See, this ability for the FMS to predict exactly where a plane will be and when is the absolute cornerstone of something called NextGen, the next generation of air traffic control. The whole vision is to create a system where every single aircraft is flying its own pre-planned, conflict-free 4D path. Imagine it. It's like a perfectly choreographed ballet in the sky, which would let us fit way more planes into our airspace and do it more safely and efficiently than we ever thought possible.
So the flight management system truly revolutionized the skies. It gave us this mind-blowing four-dimensional precision. But as we saw with that V1 example, it still needs that crucial human oversight to bridge the gap between the perfect digital plan and messy physical reality. And it kind of makes you wonder, right? As our automation gets even more powerful, even smarter, how do we make sure the next revolution in flying is not just more precise, but actually wiser?